my name is Emma, and today I will be talking to you about identifying potential pesticide dead-end transformation products of concern. This is the clicker. Great. So, as we've heard a lot today, chemicals are a huge part of our daily lives, but when we use them and they get released into the environment, they can have unintended consequences, such as harming ecosystems or contaminating water resources. And on top of that, for water contamination in particular, and what we're talking about a lot in ZeroPM, is these persistent, mobile, and toxic compounds. But what happens to the compounds that aren't persistent? Those that are broken down by metabolism, water treatment, environmental processes? Well, they form transformation products. And when we want to assess the risk of a compound, we must take these transformation products into account, because they too can be PMT compounds. Unfortunately, however, a lot of compounds lack any information at all about the transformation products that they form. So, taking our ZeroPM global chemical inventory as an example, for these over 140,000 substances, only 1,236 actually have any information in the PubChem transformation products library about the transformation products that they form. So this is less than 1% of compounds. How do we solve that problem? Well, there is roughly 3 approaches that we could take. We could carry out new experiments to try and measure new transformation products. We could try and curate existing data to get it into these databases. Or we could try predicting the transformation products that might be formed using different models. And it's these prediction approaches that I will be talking about today. So, how does transformation product prediction work? Again, there is roughly 3 different ways that this can be done. And they blend together a little bit, but on the whole they can be classified as rule-based approaches, machine learning-based approaches, and quantum chemistry-based approaches. And for environmental transformation products, the most common approach is the rule-based approach. So this is what you will find, for example, as the main component of models like NVPath and Biotransformer. And the way that this works is that the model has a list of reaction rules, and it then checks your input structure for the substructure that is listed in these reaction rules. And if the substructure is present, it applies the change that rule lists. So like you can see for this triazine substructure, the model recognizes this chlorinated triazine substructure, and the rule says, okay, we should replace this chlorine with an OH group, and the predicted transformation product is then this hydroxylated atrazine in this case. And I realize now I have mistaken in my structure, but you will forgive me for that. So, with that, the aim of this project, what we wanted to do, is to identify these potential dead-end transformation products or persistent transformation products. And the way that we defined this is then any transformation products for which no further reaction rules apply, using a beta version of Biotransformer 4.0. On top of that, we also wanted to check for our dead-end transformation products if they might be persistent or mobile and toxic as well. And finally, we also wanted to create a database of all of these transformation products. So, to do this, we started out with 324 pesticides that have been identified in European and Australian ground and surface waters. And we fed them into the Biotransformer 4.0 environmental, microbial, and abiotic modules. So you'll see these here represented with this little bacteria in the sun. And we then combined all of these transformation products into a single table to get all of the unique structures. And we then fed them back in to these biotransformer modules. So both the abiotic and the environmental microbial, and so forth for 5 generations of transformation product predictions. So the way that this looks is very large CSV files, which from a data processing and database point of view is a little inconvenient to work with. So what we started out with doing was to just separate this into one table that contained all of the unique compound information, so chemical identifiers, mass, things like that, and one table that contained all the information about the unique reactions, so the model that was used, the enzyme that might be involved, and so on. And that was then ready to be put into our database system. So we chose to work with Neo4j. And for anyone who's unfamiliar, this is a graph database, so it consists of nodes and relationships. So here we have our nodes being our compounds. These are represented by these little blue circles. And that then contains all of the compound information associated to each node for each individual compound. And the relationships are our reactions. So this then contains the information about the module that was used for the prediction and so forth that we had in our reactions table. So putting that together, we end up with this kind of network of transformational reactions. And we can then also add some extra information to this network and these nodes, such as which are starting compounds, which are our dead-end compounds, and we can also add some direct relationships between each starting and compound and their corresponding dead-end compounds to make our searching a little bit easier. So let's have a look inside this database. From our 324 pesticides, we predicted over 550,000 transformation products, and this corresponded to almost 2 million transformation reactions, which are huge numbers, but luckily, only 8,092 of these are actually dead-end transformation products by our definition. And so this can hopefully help us prioritize these transformation products a little bit, at least from a persistence point of view. Something else that we can see in our database are reaction pathways. So here you see an example of atrazine going to one of its dead-end transformation products, this dihydroxylated triazine. And actually, though I could not show it in the slide because they would have been way too small, the longest pathway we have in our database is 23 reaction steps. So this really shows you the power of this database structure to get longer reaction pathways compared to what you would normally get with on-the-fly predictions. On top of that, and I know we had a bit of a question regarding this earlier, we can also use this database to see which dead-end transformation products might be formed from multiple precursors. So here we have TFA, which has been discussed a lot today. And as you can see, it's the predicted dead-end transformation products from 12 different precursor pesticides. And of course, it's also, as a PMT compound, increasingly discussed because it's detected in multiple different environmental compartments. But it's important to remember that these are predicted transformation products, and of course this comes with its own set of limitations. So one example of that is compounds like this one, Mirex, where we can see a lot of over-prediction happening, especially as we increase the number of generations of transformation product predictions. And this seems to stem from some very generic reaction rules that these models have, like this dehalogenation rule, for example. And so our database will, of course, contain several reactions that might not occur in reality. And on the other side of that as well, there might be some data poor compounds where the model doesn't contain a certain reaction rule, and so a transformation product that might exist won't be predicted. Following that, we have also observed that this beta version of biotransformer turns out to sometimes do or cause some valency issues in the predicted transformation products. And so to combat this, we started out just filtering these using RDKit to try and remove any structures which RDKit says it cannot pass because of valency problems. And we're currently discussing this with the developers with biotransformer to try and improve this model. So after this filtering, we also mapped these structures back to their corresponding reaction rules, and it turns out that it is actually only 16 reaction rules in the model that is causing this And so we're hoping that in the final version of the model, we will be able to fix this problem. But after removing these structures, we are then down to 6,453 dead-end transformation products. So that's it for persistency. What about mobility and toxicity? And I'll be quick here because you've all seen this figure before. So for mobility, we use the CLP definition. As for toxicity, this is of course based on multiple endpoints, but we will be working with endocrine disruption. And for persistence, this is normally based on half-lives. But for our purposes, we use OPERA to predict the log KOC value and the endocrine disruption using Sept and Compara. And we assume that any compound that is a dead-end transformation product will be a persistent or very persistent compound. So, what did that result in? Well, for the compounds that fall inside the applicability domain of OPERA, 1,319 were predicted to be mobile, and out of those, 959 were predicted to be very mobile. So this is the majority of the compounds that fell inside the applicability domain of the model, which suggests that at least a large amount of our transformation products are indeed likely mobile compounds and thus likely concerning for water contamination if they are also persistent. Combining that with the toxicity results, we can then see that 1,023 compounds were predicted to be either PMT compounds or VPVM compounds. And that's still a pretty big list to work with, but it's much better than these 550,000 that we started out with. And last but not least, we also wanted to compare our model or our database to other databases. So we checked how many of our dead-end transformation products were present in PubChem. And it turns out that it's surprisingly few. It was only 98 structures. And the reason for this is still something that we are investigating. Of course, some of them seems to come from these invalid structures, but that's far from all of them. So we're still trying to see what the cause of this might be. But what we can say is that from an analytical point of view, it is very concerning if these compounds aren't present in these large structural databases, because this is often what we use to annotate our structures in non-target and suspect screening. And so if these structures aren't present in databases like PubChem, we won't identify them, even if they might be present in the sample. So, what now? Well, we'll start out by continuing to work with the Wizard Lab, who are developing Biotransformer 4.0 to make this model as good as it can be. We will then expand these predictions to the ZeroPM Global Chemical Inventory. Finally, we will make this available through a graphical user interface. And last but not least, we hope that it will be used in many different kinds of workflows, including non-targeted and suspect screening. And of course, some of this is in development already. So here's a quick teaser for our graphical user interface. It will be possible to do many different kinds of searches, such as finding the dead-end transformation products of a compound, all the compounds transformation products, and also different kinds of pathway searches. So the way that you do this is that you just plug in the chemical identifiers of the compound, such as the smiles, and you will then get a display like this for the shortest pathway search. And you can actually move these bubbles around if you like. And yeah, with that, I want to finish by thanking the Environmental Cheminformatics group from the University of Luxembourg, especially Emma Schymanski, my supervisor, as well as the Wizard Lab for working with us and letting us use their Biotransform 4 model, and the Biocore team, especially Hessam, Mustafa and Valentin, also from the University of Luxembourg, who have done great work on the graphical user interface for this. And yeah, of course, our funding, and thank you all for listening.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.